All right, let's just jump right in. Quantum mechanics is, no question, the single most successful scientific theory we have ever come up with. It's the reason our computers work, why our phones exist, pretty much everything. And yet, the whole thing is built on a foundation that, well, it seems to make absolutely no sense. It's a huge contradiction that, even 100 years later, has physicists at each other's throats.
And that right there is the real question, isn't it? This isn't just some abstract thing about math. This is a deep, really profound mystery about what it even means for something to be real. So think of this less like a physics lecture and more like a detective story. The victim, our entire understanding of reality itself.
So here's the heart of the problem. On one side, we have this set of rules, quantum mechanics, and it predicts the results of experiments with just mind-blowing accuracy. I mean, it never fails. But then you ask, okay, what do these rules actually mean? And suddenly they describe a world that seems completely bonkers. It works perfectly, but we have no idea why.
This central conflict, this huge contradiction, actually has a name. It's called the measurement problem. And you gotta understand, this isn't some minor little detail we can sweep under the rug. It is the fundamental crack in the foundation of our best theory of the universe.
So what exactly is this measurement problem? Well, it's this weird clash between two totally different sets of rules. See, on one hand, a quantum system, like a single electron, it evolves smoothly, predictably, kind of exploring all its possible futures at the same time. But the instant we try to look at it, to measure it, bam! The whole system just randomly jumps to one single outcome. Why? The theory itself just doesn't tell us.
And here they are, the two warring processes, laid out for us by the great John von Neumann. Over on the left, you've got this beautiful, continuous, deterministic dance. That's the Schrödinger equation, guiding this wave of possibilities. And on the right, a completely different beast, a sudden, violent, random snap into a single reality that just comes out of nowhere. These two things just do not belong in the same theory.
The physicist John Bell, he gave this puzzle its most brilliant and frustrating name, the shifty split. He was basically asking, where do you draw the line, right? And what exact point does a system stop being this fuzzy quantum wave of possibilities and start being a solid, classical thing we can all agree on? Is it when it hits a detector? Is it when a scientist looks at the dial? The theory gives us zero guidance, and that's a massive, massive problem.
Okay, so how do we solve this thing? Let's bring in the suspects. And suspect number one, the most famous of all, is the Copenhagen interpretation. This was the original answer, dreamed up by the founders of quantum theory. It was pragmatic, it was practical, and for a whole lot of people, it was just deeply, deeply unsatisfying. So the Copenhagen approach, it kind of dodges the question entirely. It says that wave of possibilities, it's not actually real. It's just a math trick we use to figure out the odds. It just accepts the shifty split as a fact of life, and famously told physicists to, well, shut up and calculate. Don't ask what's really going on, just get the right answer in the experiment.
But for a lot of modern physicists, that answer just doesn't cut it anymore. They don't want to just accept the mystery. They're trying to solve it. So what if we take that original Copenhagen idea, but try to, fix it? Try to actually explain where that weird split comes from.
And that leads us to this really fascinating set of ideas called objective collapse theories. The big idea here is that the collapse isn't triggered by us, our clumsy measurements. Nope, it's a real physical process baked into the laws of nature. It just happens, all on its own, spontaneously.
And listen, this isn't just some vague philosophical hand-waving. The most famous of these theories, called GRW, it actually puts numbers on it. It proposes brand new constants of nature. It says that for any one particle, a collapse is ridiculously rare. But if you have a big object, like a cat or a bowling ball, with trillions and trillions of particles, well, one of them is going to collapse almost instantly, and that forces the entire object into one definite state. This finally turns that shifty split into a hard and fast rule. It's all about size. But, of course, there's a catch. There's always a catch in physics. To solve this problem, GRW has to break one of the most sacred rules in the book, the conservation of energy, the idea that you can't create or destroy energy. See, in this theory, every little collapse gives a particle a tiny random kick, basically creating a whisper of energy out of thin air. It's an absolutely minuscule violation, but it's not zero. And that means we can actually design experiments to go looking for it. It turns a philosophical argument into real, testable science.
Okay, let's bring in our second suspect. This one takes a radically different path.
It looks at the whole measurement problem, at this messy collapse, and it asks a truly wild question. What if the collapse is just an illusion? What if it never happens at all? This, my friends, is the many worlds interpretation. It says that smoothly evolving wave of possibilities is it. That's the only thing that's real. So when a measurement happens, the universe doesn't just pick one outcome. Instead, the entire universe splits, creating a separate parallel branch for every single possible result.
So think about what this means. You measure an electron that could be spin up or spin down. The universe branches. In one universe, you see spin up, but in another, a completely identical copy of you, down to the last atom, sees spin down. The collapse is just the subjective experience you have of being trapped on only one of these branches. Both outcomes are totally real.
Now I know what you're thinking. Why on earth would anyone believe something so out there? Well, because from a physicist's point of view, it's incredibly elegant. It just gets rid of that ugly, tacked-on collapse rule. And maybe more importantly, it lets quantum mechanics apply to the whole shebang, the entire universe. When you're studying quantum cosmology, you can't have some observer outside the universe looking in to collapse it. Many worlds solves that problem beautifully. So let's turn to our third and final suspect. This one is known as pilot wave theory, or de Broglie-Bohm mechanics. And it takes a completely different road. It says, hey, what if this whole idea of a fuzzy, uncertain quantum world is just wrong? What if reality was always perfectly sharp and definite, and we just weren't seeing the whole picture?
So, according to this view, reality has two parts. You've still got the wave function, but now it acts like a pilot wave, feeling out all the possible paths. And then, riding that wave are actual, real particles that have a precise, definite position at every single moment. The reason we see all this quantum weirdness isn't because reality is weird. It's because we're ignorant. We just don't know where the particles actually are.
To make this work, the theory introduces a brand new law of physics called the guidance equation. It's basically a formula that tells these hidden particles exactly how to surf the pilot wave. And what that means, and this is a huge deal, is that all the randomness of quantum mechanics just vanishes. The universe once again becomes a perfect, predictable, deterministic clockwork machine.
So, there you have it. 3 completely different suspects. 3 totally different stories about what reality is. For decades, choosing between them felt like picking your favorite flavor of ice cream. It was a matter of taste, more philosophy than physics. But that is finally starting to change.
So let's just recap how each one deals with that shifty split. Copenhagen just accepts the mystery and builds its whole framework around it. Many worlds just blows it up, saying there is no split, it's all quantum, all the way down. And to Broglie-Bohm, it says the split is an illusion caused by information that's hidden from us. 3 solutions, 1 epic mystery.
And this, for me, is the most exciting part of this whole story. For the first time, this argument is moving out of the philosophy classroom and into the physics lab. Ideas like objective collapse make tiny but very specific predictions that are different from standard quantum mechanics, and as our experiments get more and more sensitive, we're actually starting to be able to test those differences.
You know, this has been a long, slow burn. The whole debate kicked off with the original framework back in the 20s. It was challenged by these radical new ideas in the 50s. We got new, testable physical theories in the 80s, and all of that has led to right now, today, where we are standing on the edge of using actual experiments to finally point a finger at the culprit.
Which leaves us with one last and pretty profound question. For 100 years, we've gotten by with a theory that works perfectly but makes no logical sense. As our experiments start to close in on an answer, forcing us to choose between branching universes, hidden particles, or a reality that literally pops into existence when we're not looking, are we actually ready for the answer?